Okay, welcome to the third question, which will be published tomorrow, that is on Wednesday, right, which is on 25th of September. The table shows energies. This is for 7 marks, so let me start the timer here. The table shows some of the energy levels for a hydrogen atom. So ionized state, excited state, ground state, everything is given here. Distinguish between an atom in an excited state and an atom in an ionized state. What do you mean by an atom in an excited state? It's only for 1 mark. Atom in an excited state means what? That means an atom which is present in an higher energy level, is called as an atom in an excited state. Now, what do you mean by atom in an ionized state? Which means what? An electron has been removed or added to a neutral atom, then this is called as an ionized state. Okay, so ion, what is ion? There are 2 types of ion, right? Positive ion and negative ion. When you remove an electron from an atom, that becomes a positive ion, right? And if you add an electron, it becomes a negative ion. Okay, so you cannot add a proton. Remember this, you should always add an electron or remove an electron. Okay, let us go on to the next one. Explain how electromagnetic radiation is emitted from an hydrogen atom in an excited state. So what happens? An electron which is present from a hydrogen atom in excited, when an hydrogen atom is present in an excited state, and then what does it do? It jumps down to the ground state, and as a result of it, let this energy be E2, let this energy be E1, then E2 minus E1 according to Bohr's theory, which gives you the energy difference is given as a frequency of F of a photon HF. Okay, so thus when there is a transition happening from a higher excited state to a ground state, a photon has been emitted, and this photon emitted will be emitted as in the electromagnetic radiation. This is called as electromagnetic radiation. Okay, next. When radiation of wavelength 6.6 × 10⁻⁻7 meters is incident on cold hydrogen gas, okay, some of its gas is absorbed. So what is this spectrum called as? It's called as an absorption spectra. Say the region of the electromagnetic spectra of this radiation. So you want to find out which region does it fall into. Now you see, it is showing you a wavelength of 6.6 × 10⁻⁻7, which corresponds to how much? Which corresponds to 6600 angstroms or 660 nanometer. Which region does it correspond to? We know that if at all if you have a wave, a spectra or a line which falls from 400 to 700 nanometers, it falls in between 400 to 700 nanometer, this will be corresponding to your visible spectrum, right? This everyone knows it. So it belongs to visible spectrum. 660 lies between that. This, I presume, this will be closer to your red color line. Okay, let us move on to the next question. Determine the initial and final state of the hydrogen atom that are involved in this absorption. Initial and final states. Now, how do we do initial and final states over here? So what we do is, let me go back to the table that has been given here. There is n equal to 3, n equal to 2, n equal to infinity, everything is given over here. Energy in terms of electron volt is given here. But we have only wavelength here. Now what we will do is, we will find out the energy difference. Delta E is equal to hc by lambda, which should be, what is hc? 12.4 kilo electron volt angstrom. It's a shortcut for hc. Okay, I hope you remember this one, which you have done it in the class also. Lambda. What is lambda? 660 nanometers. 660 nanometers are 6600 angstroms. I will use this one, which is easy for me to work with. Angstroms. Angstrom goes away. And I can now write this as 12.4 into 10 cube electron volt divided by 6.6 into 10 cube. Right? So this 10 cube also goes away. So what am I left out with? 12.4 divided by 6.6 electron volt. So what is this value? Let us find out. So it becomes easy for us when you go adopt these kinds of shortcuts instead of using calculators every time. Okay, 12.4 divided by 6.6 is 1.88. 1.878, which is 1.88 electron volt. This is what we have. Now let me go back to the table. See, when there is a table given, you have to use this one here. Now what did I say? I said that when you have a wavelength lambda, that should be equal to energy difference between any 2 levels, right? So let us find the energy difference between these two. What is this value? 13.6 minus 3.4. Definitely this is 10.2 electron volt. If I do this math, I will get this value. Now if I do the difference between these two, what is it I get? This is 10 minus 1 is 9, then 14 minus 5, 14 minus 5 is 9 over here, 14 minus, is it 14? No, it's 13 here, 13 minus 5 is 8 over here, and then this is now 2, 2 minus 1 is 1, 1.89. 1.89 is the difference between these two. Now if I take these two also, okay, all the combinations will take. So if I take this will definitely be 6, 0, so 10 minus 1 is 9, then 5 minus 5 is 0, and then you have 13, 4, 12 minus 1 is 11. I can do it using calculator also, right? Why should I do all these things? Let me do it accurately. 13.6 minus 1.51, 12.09. See, I made a mistake here. So this should be 12.09, 12.09. So these are the only difference in energy levels that we can have. Now why did I find a difference level? Because when you have an energy difference, there will be a photon being emitted, right? We already found out the photon here. Already photon is been given over here. We found out the energy levels. What is the energy difference here? 1.88 electron volt. Which does it correspond to here? It corresponds to 1.89 here. So therefore, the electron is translated from n equal to 3 to n equal to 2. Okay. Now, if it is an emission spectrum, n equal to 3 to n equal to 2 is good. But this is an absorption spectrum here, because cold hydrogen gas, it was absorbed. So initial and final state of the hydrogen atom that are inward. This is for 3 marks. Word it appropriately. First mark will go here. Second mark will go for comparison. Comparing the energy differences from the table given. We found that for n equal to 2 to n equal to 3. So it does not happen with n equal to 3 to 2. Okay. We found what? Delta E is equal to 1.89 electron volt. So which closely matches with this, and thus the initial and final states are, this is your initial, this is your final state. This is what you need to mention. Okay. Let us see. Yeah, this is the last question in this. Okay. Thank you.